So let us now try to do a correlational analysis. You know that the correlation is a measure of association between two variables. And so the only thing to take care of here is when we are doing multiple correlation. So for example, if we are comparing three variables in a data set, like here, if we have the GPA, the CRTC scores, and the height. So if you have three variables that we are taking care of is the alpha value, that is the level of significance. So I will talk about that in just a minute, but here, so if we are looking at correlation, which I just said is a measure of association between the two variables, the value of the correlation coefficient can vary from 1 to -1. So 1 is a very strong correlation, very strong positive correlation, rather a perfect positive correlation. 0 indicates no correlation, and a -1 is again a strong correlation, but it's a negative, perfect negative correlation. So if you look at the correlation values of 0.1, 0.3 and 0.5. 0.1 is small, 0.3 is medium, and 0.5 is large. So 0.5 to 1 is large, or -0.5 to -1 is large correlations. The default null hypothesis for correlation is 0, which means that there is no statistical correlation in the population. What it is when you look at multiple correlations, that is what we are looking here. When we look at multiple correlation, there is a correction that we have to apply that is called the Bonferroni correction, which I will talk about. So this is really important to remember, the Bonferroni correction for the correlation thing. So we have three variables. When we choose our value of alpha, our usual value of alpha is 0.05. But because we have three variables, we actually divide the alpha value by 3, and that is 0.017. So this means I reject my null hypothesis if the p-value for the correction is less than 0.017 or equal to. So equal to or less than. So here my p-value is, so if I have 4 variables, I'm going to divide my 0.05 by 4. If I have 5 variables, I divide by 5. So this is really very important to know, because this is called Bonferroni correction. So we are going to talk about, to see whether there is a correlation between the GPA or the corresponding city score that they have, that is the corresponding city score, and the height. So I've just chosen 3 variables. I've just come up with a data set to explain this. But you could be looking at correlation between any of the variables that you want to. So here's my research hypothesis. Are there statistically significant correlation among students' standardized scores, that is the GPA, the city scores, and the height? Null hypothesis obviously is no statistical significance. That means the correlation is 0. Among the scores, student standardized test scores, GPA, CRTC scores, and height. As I explained, my level of significance, the alpha value or the p-value here, well, the p-value actually is called the alpha value when I am doing my correlation. It is going to be 0.017. So I reject the null if the alpha value is less than or equal to 0.017. So the most general correlation that is done is the Pearson's R is the most general correlation, and there are 2 assumptions to be done for the Pearson's R. the data are collected at least at the interval level. The sampling data is normally distributed. Each variable are normally distributed. So except for obviously the dichotomous if you have, but the sampling, the interval level data is normally distributed. And I said two, actually three, linearity of the sampling variables with each other. So those are the criteria that we have to meet if we are doing a Pearson's R. So remember how we check for, so the first assumption that the data is at the interval level is satisfied because here is my data set and you have a spreadsheet of it, and the SAV is, if you look at it, all of these three, the GPA, the city scores, the height are actually in the scale level. So yes, that one is satisfied. I'm going to use this a little bit. And so now I want to check whether the normal distribution, so I want to check whether it is at the interval level. Yes, the normal distribution is n greater than equals to 30. Let's check that. So yes, it is 40. So my n is greater than equals to 30. I have more than 30 data set. I also have to check the KS test if it is 0.05 and more, and I have to look at the scatter plot to see whether the data is linear or not. So let us now do the scatter plots. So to do the scatter plots, I'm going to go to my data. I'm going to go to graphs, legacy dialogs, scatter plots. I'm going to click simple scatter plot, click define. And as you can see, these are my three variables. So I choose GPA on the first axis. I choose this on the x-axis. And you're going to be wondering, where does the height go? Well, we will create scatter plots with height. Also, we are going to keep switching them and creating the scatter plots. So we'll have three scatter plots. So I'm going to press OK. And here is the scatter plot. I double click on this and I want to make sure that I have linear clicked. And then I close, and so if you can see this, this is my linear. So somewhat, some points are above, some points are below, but it is kind of linear, right? So let's go back to, so now we are going to change, the graphs or not analyze, we define. And so what I did was, we had the GPA first. This is how we had it. So we had the GPA and the CRTC scores, and I took away this and put my height in there. I pressed OK and I got this graph. Once again, I double click, I did the linear, I want to make sure. So even though these points don't form a linear thing, if you look at it, some of the points are above and below. So they are kind of having a line of best fit. So I go back to my graphs, I go back to scatter plots. And so I have done between GPA and CRT, I've done between GPA and height. So now I need to do between CRT and height. So I press OK. I get this graph. Once again, I look at the linearity. And this is what it looks like. So it is actually telling us the relationship between each of these variables, the correlation. And so out of these, the one that is the most following a straight line is obviously the GPA and the city scores. So I am going to, so here are all your charts. Here is this one, and this is the line one, and this is the other one, and this is, so here is my result. So one of the things to notice is I did not do any, not checking normality using histograms or using the KS test, because the sample size in this example is obviously greater than 30, it is 40. So because of the central limit theorem, it says that if your sample size is more than 30, then the sampling distribution is automatically normal. So I do not need to check anything else for normality of the sampling distribution. So so here is the report on the assumptions. An analysis of variables in the data set indicated that they were all collected at least at the interval level. So they are at the interval level. A visual analysis of the scatter plot of GPA and the CRT scores, then the GPA and the height, and then the height and the CRT scores indicated linearity of correlation. I assumed normality for the sampling distribution because the sampling size is greater than 30 according to the central limit theorem. So that is all you need to do for the assumptions. So now that we have that, let us do the correlation analysis using Pearson's R and correlate the bivariate. So we are going to correlate and select all the three variables. So let me go back to my data and I want to do analyze and I want to correlate. I'm going to do my Pearson's R. So I am going to select all my three variables because this is the Pearson that I want to do. I want to make sure and put it in the dialog box. I want to also make sure the Pearson is checked, and then the significance is I'm doing a two-tailed. And so if our Pearson's assumptions were not met, we would have done Kendall-Stowe or Spearman's. But here, our Pearson's assumption is met because one of the big things is it is at the interval level. So I'm going to press OK. And here is my correlation. So I have put this table. Here is that table, the matrix table. So for GPA, Pearson's correlation R is with CRTC is 0.963. That is very close to 1, which shows a very strong correlation with that one. So, and then if I look at CRTC, well, GPA with CRT, but GPA with GPA will obviously be 1 because you're correlating the GPA with itself. But when you look at this with the height, that is 0.188. So that's like 0.19, which is very low. So if I look at the city scores again, with itself will be 1, but with GPA it is. So high city scores, it is a positive correlation. So what I can say is high GPA is high city scores, but there is no correlation with the height, which is probably even from the scatter plots, you would have guessed that they would have a correlation because they were nearly following the line, but these were all over the place. So there wasn't going to be any correlation between height and GPA or height and CRT scores. But between GPA and the CRT scores is a correlation. So p-value, if I look at the p-value, then it is 0.000, which it's never all 0. There must be some digits, but it is less than 0.017. So we can reject the null between the GPA and the CRT scores to say that there is a correlation there. However, we cannot reject the null between CRT scores and height or GPA and the height. It is not statistically significant because the p-value between height and GPA is 0.244, which is more than 0.01. And then between height and CRT scores, it is 0.203, which is again more than 0.01. So we cannot reject. So we have to determine the effect size. Pearson R is already an effect size. So here you do not even have to do. And if you look at this, this is your effect size. You already have it. It is a high effect size. It's a large effect size. That's what it is. So that is a really simple thing to do. So here is my report. There was a large statistically significant correlation between GPA and the CRT score. R is small and italicized. parentheses 40. Where am I getting the 40 from? This is my n, equals to 0.96, two values. P is less than 0.001. Remember, this is 0.000. I could put 0.001 or like 3 zeros and a 1 also, but there has to be a 1 somewhere. It is not completely a 0. However, there were neither statistically significant correlation between GPA and height, nor between height and the CRT scores. So this is what you have. You are not reporting the effect size in this. Effect size is the Pearson's R. You will have that in your assignment, but you do not put that in the report over here. This is all about correlation. And I wish you all the best. If you have any questions on the assignment, please do not hesitate to ask. Have a great day, guys.